A black hole is a region of space-time exhibiting gravitational acceleration so strong that nothing, no particles or even electromagnetic radiation such as light can escape from it. The theory of general relativity predicts that a sufficiently compact mass can deform space-time to form a black hole. The boundary of the region from which no escape is possible is called event horizon. Although the event horizon has an enormous effect on the fate and circumstance of an object crossing it, no locally detectable features appear to be observed. In many ways, a black hole acts like an ideal black body as it reflects no light. Moreover, quantum field theory in curved space-time predicts that event horizons emit Hawking radiation with the same spectrum as a black body of temperature inversely proportional to its mass. This temperature is on the order of billions of the Kelvin for black holes of stellar mass, making it essentially impossible to observe. Objects whose gravitational fields are too strong for light to escape were first considered in the 18th century by John Michael and Pierre Simon Laplace. The first modern solution of general relativity that would characterize a black hole was formed by Carl Schwarzschild in 1916. Although its interpretation as a region of space from which nothing can escape was first published by David Finkelstein in 1958. Black holes were long considered a mathematical curiosity. It was during the 1960s that theoretical work showed they were a generic prediction of general relativity. The discovery of neutron stars by Joshua Bell Burnell in 1967 sparked interest in the gravitational collapsed compact object as a possible atmospheric reality. Black holes of stellar mass are expected to form when very massive stars collapse at the end of their life cycle. After a black hole has formed, it can be continued to grow by absorbing masses off from its surroundings. By observing other stars and merging with one other black holes, supermassive black holes of millions of solar masses may form. There is a consensus that supermassive black holes exist in the center of most galaxies. The presence of a black hole can be inferred through its interaction with the other matter and with the electromagnetic radiation such as visible light matter that falls onto black hole can form an external acceleration disk heated by friction, forming some of the brightest objects in the universe. If there are other stars orbiting a black hole, their orbits can be used to determine the black hole's mass and the location. Such observations can be used to exclude possible alternatives such as neutron stars. In this way, astronomers have identified numerous stellar black hole candidates in binary systems and established that radio source known as Sagittarius A at the core of a Milky Way galaxy contains a supermassive black hole about 4.3 million solar masses. The idea of body is so massive that even the light could not escape from, briefly proposed by astronomical pioneer and English cryptographer John Michael in letter published in November 1784. Michael's simplicity calculations assumed such a body might have the same density as the Sun, and concluded that such a body would form when a star's diameter exceeds the sun's by the factor of 500 and the surface escape velocity exceeds the usual speed of light. Michael correctly noted that such supermassive but non-radiating bodies might be detectable through their gravitational effects on nearby visible bodies. Scholars of the time were initially excited by the proposal that giant but invisible stars might be hidden in plain view, but enthusiasm dampened when the wave-like nature of light became apparent in the early 19th century. Formation and evaluation. Given the bizarre character of black holes, it was long questioned whether such objects could actually exist in nature or whether they were merely pathological solutions to Einstein's equations. Einstein himself wrongly thought black holes would not form because he held that the angular momentum of collapsing particles would stabilize their motion at some radius. This led to general relativity community to dismiss the all results to the contrary for many years. However, a minority of relativists continued to contend that black holes were physical objects, and by the end of the 1960s, they have persuaded that majority of researchers in the field that there is no obstacles to form the of an event horizon. Penrose demonstrated that once an event horizon forms, generally relativity without quantum mechanics required that a singularity will form within. Shortly afterwards, Hawking showed that many cosmological solutions that growth. Once a black hole has formed, it can continue to grow by observing additional matter. Any black hole will continually absorb gas and intersectal dust from its surroundings. This is the primary process through which a supermassive black hole seems to have grown. A similar process has been suggested for the formation of intermediate mass black holes found in globular clusters. Black holes can also merge with the objects with such as stars or even other black holes. This is the thought have been important especially in the early growth of supermassive black holes which could have formed from aggregation of many smaller objects. The process has been proposed as an the origin of some intermediate black holes. Evaporation. If the Hawking theory of black hole radiation is correct, then black holes are expected to shrink or evaporate over time as they lose mass by the emission of photons and other particles. The temperature of this thermal spectrum is proportional to the surface gravity of the black hole, which for a Stephenson child black hole is inversely proportional to the mass. Hence, large black holes emit less radiation than small black holes. This topic is end for today. If you like this video, please like, share and subscribe my channel. Thanks for watching my video. Thank you.